Myself Prayak Patel, working as Assistant Professor in IT/ICT Department of LG Institute of Engineering and Technology. Now in today's video lecture, I will discuss about the max flow mean cut theorem. So here we discuss about what is the possible maximum flow in a network and what is the minimum cut. So for that, one theorem is called the max flow mean cut theorem. So here theorem is like this: for a transport network n equal to VE, the maximum flow value that can be attained in n is equal to the minimum capacity over all cuts in a network. So maximum flow in a network is equal to the minimum cut possible in a network, or addition of all the minimum cut is capacity. So it is called the minimum cut. So this theorem we understand using the example. So see here in this example, consider the network n equal to VE in this figure, where consider the f of e equal to 0 for each and every edge. So here we can say that the 10 0, that means 10 as a capacity, 0 as a flow. So for the initial flow of all the edges is considered equal to 0. Now after that, the capacity of the edges is like AB capacity equal to 10, BZ capacity equal to 10, AD capacity equal to 10, DZ capacity equal to 10, and D to B capacity equal to 1. So this is a given capacity for the network and flow equal to 0 for all edges. Here we can say that if we use the directed path from A to B and B to Z, so capacity of A to B and B to Z is a 10 minus 0, 10 minus 0, that means 10 and 10. So from A to Z we use the A, B, Z path, then total flow equal to 10. Same way for the another path A to D and D to Z. So here capacity for A to D and D to Z equal to 10 and flow initially equal to 0. That means we increase this flow by 10. So 10 10 for A to D and 10 10 for D to Z. So here we can say that first is represent the capacity, second is represent the your flow for the network. So this is a capacity for the total maximum capacity of this flow equal to 20. So CPP dash equal to, we can say as the 20. Now P equal to A and P dash equal to remaining all elements. So here one cut, if we remove the any edge, then A as a one part and remaining all node in a second part. So this is an example of the maximum flow. Now after that, here consider the another path. If we use the path as a to B, B to D and D to Z. So our flow in third figure is like 10 1, means 10 as a capacity, 1 as a flow. Then 1 0 as a B to Z. Then here D to Z is also 1 and A to D is also 1. So for all the edges we consider the path as a capacity equal to 10 and flow equal to 1 for outer all edges. Now for the inner edge B to D, 1 0, 1 as a capacity, 0 as a flow. Now see here, if we move from our path like this, see here in this path, if we consider the path as a to B, then B to Z, then we can say that the one increment is done. Now for the another path A to D, D to Z, also we increase by 1. So total 20 times we perform this operation, then we will get the value as a 20 as a maximum flow. Now after that, consider the next definition is a usable edges. Now here for usable edges, let n equal to VE be a transport network with flow m. So here start to the construct a breadth first search spanning tree T for network n. Here use the undirected graph using the source A as a root, and we can consider the each and every vertices of this graph. Now here, while the sink Z is not a vertex in T, that means T is a breadth first search spanning tree. So if sink Z is not available in a tree, then we can say that in breadth first search spanning tree Z is not available. Let E equal to VW be the newest edge appended in the constructions of T, with V in the present tree and W is in the new vertex. So V is available in a tree and W is a new vertex in a tree. Then we can say that the VW as a edge. The edge E is called the usable if E equal to VW with flow of E less than capacity of E, or second condition is E equal to WV with f of E greater than 0. That means If the forward edge is available, then we can say that the flow is less than capacity. If backward edge is available, then flow of E is greater than 0. Then we can say that our this particular edge is usable. So if flow is less than capacity for forward edge, then it is usable. If flow is greater than 0 for backward edge, then it is usable. So this is a definition of usable edges. Now here for understanding the max flow mean cut theorem, we use this algorithm. Name of the algorithm is Edmonds-Karp Algorithm. Now first step of this algorithm is place the source node A into the set P. So initially in set P, one node as a source node A. Assign the label space 1. That means initially assign the source node A as a labeling blank 1. That means this parent node of the source node is nothing and 1 as a your sequence number. Now set the counter I equal to 2 for the next node. Now second step number 2, while the sink Z is not in P, then we apply the next step as a if there is a usable edge in N. So we check the particular edge is usable according to previous definition of usable. Let E equal to VW be usable with labeled vertex P having the smallest count assignment. So here consider the sequence number, count number, and according to count number we have to follow the sequence. If W is unlabeled, then we can use the W. Then label the W with VI. So V as its parent and I as a count. Place W in P. So initially P having a one node as I, now we add W in P. After that, next step is a increase the counter I by 1. So increase the value I by 2, then 3, then 4, then 5 like this. Now else part. Return the minimum cut PP dash. And last step as a step number 3. If Z is in P, start with Z and backtrack to the using A as a your source node. So here we can say that the first component of the vertex label. So here according to step number 3, we execute the algorithm as a last part. If Z is in P, means your sink is available in your P part, then stop the process and start the backtracking. Now after that, another algorithm for the max flow mean cut is Ford-Fulkerson's algorithm. So now in this algorithm, step number 1 is define the initial flow f on the edge on N by f of E equal to 0 for each E belongs to E. That means initially flow of each and every edge equal to 0. Step number 2. Repeat the following step. Apply the Edmonds-Karp algorithm to determine f augmenting path P. So find the path according to our previous algorithm. Then delta P equal to minimum of delta E. That means find the minimum value out of all the delta E and it is called the delta P. So increase the flow according to delta for each E belongs to P. If E is a forward edge, then flow of E equal to flow of E plus delta. Now else part. In else part, if your edge is a backward edge, then what we have to do? Flow increase like this, flow of E equal to flow of E minus delta P. So decrement by delta P. Until no f augmented path P can be found in N, we can repeat this step. So repeat the maximum flow N. Return the maximum flow. Now step number 3. Here, return the minimum cut PP dash from the last application of the Edmonds-Karp algorithm where no further f augmented path could be constructed. So if no any path is possible, then our last cut is considered as a flow as a minimum cut PP dash. So find this using example. So understand this two algorithm using this example. So here this is a given graph or given network. Now in this network, initial flow of each and every value equal to 0. For each and every edge, we write the two component. First component as a x, second component as a y. So x that means capacity, y that means flow. So here x is a capacity, y is a flow, and initially flow for each and every edge equal to 0. Like for 0, for as a capacity, 0 as a flow. Now after that, according to step number 1 of the Ford-Fulkerson algorithm, here we use this algorithm and find the path. So see here, A as a source node. So initially assign the value or label to the node A as a node number. Then blank space and 1. That means A as a your initial node, source node, and 1 as a count. Now after that, visit the node one by one in alphabetical sequence. So after that, visit the node B, because here 3 neighbor node is available for the node A, B, D and G. So visit one by one in alphabetical order. So first we visit the B. So A to B. Now for the B, what is the labeling process for the B? For the B, we consider the increment I value by 1. That means old value of I equal to 1. Then new value of I equal to 2. Count equal to 2. Now next, what is the parent of the B? Parent of the B equal to A. So here we write in place of B, we write BA2. That means A as a source node of the B and 2 as a count sequence number. Now after that, we visit the next node as a to D. So D count as a A3. Now next we visit the node A to G. That means count for the G, labeling for the G as a A4. So count increase by 1. Now after that, after visiting B, D and G, we start the count from here. We consider first count as a 1 and all the neighbor of 1 is completed. So now after 1 we consider the count as a 2 and 2 available at the node B, BA2. So see here, find the next child of the node B. What is the path from B to next node? So B to J, one path is possible. So labeling J as a B5. Now after that, no any path possible from B. So check for the D. So D to Z path is possible. So write the ZD6 as a labeling for the node J. And after that, we can consider the, here we reach at the sync node J. So stop the process. So see here, this is a path and here we stop the process at the Z node. Now after that, backtracking is done for the Z to your source node. So what is the path? Check here what is the path from A to Z or Z to A. So using the backtracking, we find the path is like that, Z to A as a to D, D to Z, or reverse node we can consider as a Z to D, then D to A. So this is a path from A to D, D to Z. Now here check the capacity of this path. So here for the capacity, we can find the path from A to D, D to Z, and here capacity delta P, increase capacity by delta P. So delta P equal to minimum of 3 minus 0, 5 minus 0, because in this path 2 ACs is available. So here minimum value is 3. That means we can increase the flow as a 3. So here we increase the flow 3 in this our particular network. In the fourth figure, we increase the first flow A to D as a 3 and D to Z as a 5. Now after that, same process can be repeated. So once again we assign the labeling from source node to your sync node. So first A1, then visit the B as a A2, then visit the, here already D is not visited, not usable, because here capacity and flow is same. So A to D path is not possible. Now A to G. So A3 labeling for the G. Now after that, start from the B. So B to J consider as a B4. Now from the G we start the G to H. So labeling as a G5 for the node H. Now after the node H, here we consider the node sequence number, count number as a 4. So JB4. From the JB4 we start the visiting, then visit the node case J6. Now after that, start the node for the G5, HG5. So HG5 to visit the H7, that means DH7, then MH8. After that, from K to any path is possible. So here K to D path is available, but this is not usable because already we visit the node D. That means we cannot use the path from K to D. That's why we visit the node D to Z. So D to Z, Z sequence as a D9. Now we reach at the destination node at the Z node, then we start the backtracking. How we can reach the Z? So source node of the Z is a D, source node for the D as a H, source node for the H as a G, source node of the G as a A. So our path is like this. A to G, G to H, H to D and D to Z. Now for this path, find the delta P value. That means subtraction of capacity and flow. So 3 minus 0, 6 minus 0, 4 minus 0, 5 minus 3 equal to 2. So here minimum value equal to 2. That means we can increase the flow by 2 in this sequence. So our new flow value is equal to 5 because old flow value is already 3 plus 2 equal to 5. So see in the last figure, we increase the flow by 2 in our network A to G, G to H, H to D and D to Z. So this is a sequence for this network. Now after that we can apply or find the another path in this network. So using this, once again start from the node A. So A is a source node. Now A to B. Then B to, we can A to B and A to G. Both paths are possible because flow is not same as a capacity. So labeling B as a A2, G as a A3. Now after that start from B. So B to J is possible. So JB4 is a next labeling for J. Now from G to H is possible. So HG5 as a labeling 5. Now next from J to any path is possible. Yes, J to K is possible. So K labeling as a J6. Now from H to path is possible. Yes, H to D as a labeling 7, H to M as a labeling 8. So MH8 as a labeling. Now after that from K to any path is not possible. From D to any path is not possible. So we start the process from N. So M to N is possible. So labeling as a M9 for the N. Then next labeling for the Z as a ZN10. So we reach at your destination node Z. Then find the backtracking and path. So backtracking is Z reachable from N, N reachable from M, M reachable from H, H reachable from G and G reachable from A. So consider this path and find this path. Now find the delta P value. That means increase the flow. What is the delta P value? So for the delta P value we find the 1 as an increasable flow and increase this flow in this network. Then we find the last figure number 10 as a increases flow as a to D 3 3, then 6 3, then 4 1, then 8 1, then 7 1. Now this is a network for the flow. Now here our flow is like 6. Now after that we find the another flow, another path. It is possible. So see here another path has a to B, same way. Then B to J, then J to K, then K to D, D to H, H to M, M to N, N to Z. So this another path is also possible. Same way we can assign the labeling for each and every node and find the path. Now here what is the value of delta P? What is the increasable flow in this network? So see here in this network we can say that increasable flow equal to 1. So here we increase this flow as a minimum value of the delta P equal to 2. So we increase the flow by 2. So delta P equal to 2. Now after that, resultant figure is like this. So what is the flow value? Maximum flow value. Maximum flow value old equal to 6. But new maximum flow value equal to 6 plus 2 equal to 8. And in last figure, we already increased the value of the flow in each and every case according to our path A to B, B to J, J to K, K to D, D to H, H to M, M to N and N to Z. So this is your network. Now after that, maximum flow we can find as a 8. Now how we can find the cut? So for the cut, once again we start the same process and find the path. If we not reach at the destination point, then we can say that this is a cut. So for that, here start the process from A. So A labeling as a 1. Now A to B path is possible, A to D and A to G is not possible. So A to B, so B labeling as a A2. Now B to J, J labeling as a B3. Now J to K, K labeling as a J4. Now K to D, D labeling as a K5. Now from the D any path is possible. So here D to Z is path, but here already used. D to H is also not available because not usable. Here flow is backward edge and backward edge flow equal to 0. That means not usable. So here we can say that no any path possible from D. That means we can say that here cut is possible. That means in one part of your network, P as a B, J, K and D, and another part as a remaining element. So we can say that here we cut the element as a one part P as a B, J, K, D, and remaining as a second part as a P dash. So here we can also find the maximum flow as well as minimum cut. So this is a minimum cut, P as a B, J, K, D, P dash as a G, H, M and J. So in this second figure, we see that one dash line, dotted line is considered as a cut. So this is a simple example of the maximum flow and minimum cut. Here maximum flow equal to 8 and cut is available like this. This cut considered as a C1 cut. So in this lecture we can understand how we can find the maximum flow and minimum cut. Thank you for watching this video.